Ever get that feeling? You're hearing all this talk about big, complex ideas, maybe in AI or something, and you just wish someone would cut through it all.
Yeah, just give you the essentials, the stuff that actually matters.
Exactly. So, welcome to the deep dive. We do that work for you, sifting through sources to pull out the key insights.
That's the plan. We guide you through it. And today, we've got quite an interesting topic lined up. We've been digging into a survey paper from RF.
Oh, yeah. What's it on?
It's all about transfer learning in AI. It's a pretty dense paper, covers loads of different approaches, applications. It's a big area.
Okay, transfer learning. So our mission today for you listening is to unpack that, give you a clear idea of what transfer learning actually is, why it's important, and maybe touch on some key methods without, getting lost in the weeds.
Right. We want you to come away with a solid understanding, fast, not a headache from too much technical jargon.
Perfect. Oh, and actually, before we dive in, if you are looking to go deeper into AI later, there's a discount for the AI course over at rajamanicum.com.
Oh, right.
Yeah, just use the code QPT when you check out. Okay, so rajamanicum.com, code QPT. Got it. Let's start at the beginning then. What is transfer learning?
Basically, transfer learning is about getting better at learning something new, a target task. By using knowledge you gain from learning something different but related, a source task.
Okay, like knowing how to ride a bike helps you learn to ride a scooter faster.
Exactly like that. In machine learning, we take the knowledge, maybe patterns or features learned from a source domain, and we apply it to improve how a model learns in a target domain. And the big advantage really is it often means you don't need nearly as much labeled data for that new target task.
Right, which is often the bottleneck, isn't it? Getting enough good data. So if we trained an AI on, say, millions of cat photos, that's the source, could we use that knowledge to help it recognize leopards, the target, even if we only have a handful of leopard photos?
Yeah, precisely. That's the core idea. We talk about source domains and target domains, and each has its own task. And the knowledge we transfer, it isn't just from labeled data. It could be learned from unlabeled data or even from a pre-trained model itself.
Okay, so maybe we have tons of labeled data for identifying different makes of cars, but very little for trucks.
Yeah.
Transfer learning could leverage the car knowledge to speed up learning about trucks.
Exactly. And a related concept here, which is really important, is domain adaptation. This is basically the process of adjusting things so the source knowledge is more useful for the target problem.
Adjusting how?
Well, maybe the car photos were all taken in daylight, but the truck photos are mostly at night. Domain adaptation techniques try to bridge that gap, reduce those differences so the car knowledge translates better.
Got it. Making the source knowledge more compatible, kind of. So it sounds like there could be lots of different situations and ways to do this. How do people categorize all these approaches?
Good question.
Yeah.
The paper lays out a few main ways. One is based on the labels you have. So transductive transfer learning is when you only have labels for your source data. None's for the target.
Okay.
Inductive means you do have some labels for the target data too. And then there's unsupervised, where you don't have labels in either domain.
So it depends on how much help you have for the new task, basically.
Pretty much, yeah. Another way to categorize is by looking at the feature space and the label space. Are they the same in both source and target or different?
What's that mean, feature space?
Like, are you dealing with the same kind of input data? Pixels from images in both cases. That's homogeneous transfer learning. But if you're trying to transfer knowledge from, say, text descriptions to image recognition, the features are totally different. That's heterogeneous.
Ah, okay. Same kind of problem structure versus fundamentally different data types. And then what about the actual methods used? You mentioned approaches earlier.
Right. The survey groups the methods themselves into 4 broad categories. First up, instance-based.
Instance-based.
Yeah, the idea here is to focus on the individual data points, the instances from the source domain. You basically try to figure out which source examples are most relevant to the target task and give them more weight or importance.
Like cherry picking the most useful examples from the source.
Sort of, yeah. Or at least reweighting them. Then second, you have feature-based approaches. These ones work on transforming the features themselves.
Transforming them how?
Well, the goal is to find a new representation of the features that works well for both domains. Sometimes it's asymmetric. You change the source features to match the target. Other times it's symmetric. You try to find some common shared feature space and map both source and target data into that space.
Okay, so finding a kind of common language for the data.
Exactly. The third category is parameter-based. Here, you're transferring knowledge by sharing or reusing parts of the machine learning model itself, specifically its parameters, its internal settings.
Like taking an engine tuned for one car and using it as a starting point for tuning an engine at different cars.
That's a decent analogy, yeah. You might take parameters learned by a big model trained on general images and use them to initialize a model for a specific medical imaging task, for example.
Save a lot of initial training time, I bet.
It can, definitely. And the last category is relational-based. This is more specialized, focusing on transferring knowledge about relationships between data points, which is common in things like social networks or knowledge graphs. Figure 2 in the paper actually gives a nice visual overview of all these.
Okay, instance, feature, parameter, and relational. That helps structure things. Now, the survey also mentioned looking at this from a data-based perspective. What's the focus there?
Yeah, the data-based view really zooms in on manipulating the data itself. Figure 3 shows some strategies. A lot of it comes down to trying to make the source and target data sets look more similar statistically.
Which sounds like domain adaptation.
Exactly. It's a core part of it. And from this data perspective, the two big strategies are the ones we touched on: instance weighting and feature transformation.
Right. Instance weighting giving more importance to certain source data points.
Especially if the overall distribution is different. Like the paper gives an example. Imagine diagnosing cancer. Your source data might be mostly from elderly patients, but your target is younger patients. The disease might manifest differently.
So you'd want to maybe downweight the elderly patient data or upweight the few younger source patients you have when adapting to the target.
Precisely. You adjust the weights to minimize that difference in distribution. That's an algorithm mentioned, TradeABoost, that does this iteratively, adjusting weights as it learns.
Okay. And the other database strategy was feature transformation. Let's dig into that more. What are the main goals and techniques?
So with feature transformation, you're trying to find a new way to represent the data features, a way that makes transferring knowledge easier. The objectives could be reducing the statistical difference between domains, like we said, but also maybe preserving important properties of the original data, or finding direct links between specific source and target features.
And how do you actually transform them?
The paper talks about 3 types of operations: augmentation, creating new features; reduction, selecting a smaller subset of important features; and alignment, which is about mapping source and target features into a space where they are closer together.
Alignment seems key for bridging that domain gap.
It often is. And to know how well you're doing, you need ways to measure that gap, right? To measure the difference between the source and target distributions. Table 2 lists some metrics.
Like what?
Well, a really common one is MMD, maximum mean discrepancy. It sounds complex, but the idea is to measure the distance between the average source data point and the average target data, but in a special kind of high-dimensional space called an RKHS.
Okay, so a mathematical way to say how far apart are these two data sets on average?
Basically, yeah. And techniques like kernel mean matching, KMM, actually use MMD to help figure out those instance weights we discussed earlier.
Ah, it connects back.
Yeah.
Clever. But what if you don't have target label? How do you measure differences related to specific classes or outcomes if you don't know them in the target?
That's a huge challenge in unsupervised adaptation. One common trick is pseudo-labeling.
Pseudo-labeling.
You train a model on your source labeled data first. Then you use that model to predict labels for your target data, even though you don't know the real ones.
So you're generating best guess labels for the target data.
Exactly. They're pseudo-labels. They won't be perfect, but they give you some handle on a target structure. Then you can use those pseudo-labels to estimate things like the conditional distribution difference, how different the features are for things predicted as class A in the source versus the target, for instance. You often use modified MMD formulas for that.
Using your current knowledge to make an educated guess, then refining based on that guess. Makes sense. What are some specific feature transformation techniques mentioned?
There are quite a few groups. One is subspace learning, or feature alignment. The idea is to project the data into a lower dimensional space where the domain differences are reduced.
Finding a simpler view where they look more alike.
All right. Transfer component analysis, TCA, uses MMD to find such a subspace. Then you have methods using autoencoders, types of neural networks like MSLDA or SDA. They learn compressed representations that are hopefully robust to domain shifts.
Autoencoders seem popular for this.
They are. There's also geodesic flow kernel, GFK, which is interesting. It thinks about the path between the source and target distributions in a geometric way and tries to align them along that path. And methods like SFA and CDSC use graph theory concepts to align feature structures.
Wow, okay. Lots of different mathematical angles. Any others?
Yeah, feature clustering is another approach. Instead of individual features, you look for groups or clusters of features that represent higher level concepts. CoCC does this for text, using word co-occurrence. TTP-LSA and CDP-LSA are related methods for finding shared topics across text domains.
So finding the underlying themes that connect different documents.
Exactly. And there's also pivot-based transformation, which relies on identifying features that are inherently common or act as pivots between the domains. And again, autoencoders often pop up here too, since they learn these abstract representations.
Okay, that gives a good sense of the data-centric side. What about the model-based strategies? How does knowledge transfer happen at the model level?
Right. Model-based approaches focus directly on the models. Figure 4 gives an overview. You see strategies like parameter sharing, making parts of the source, and target models literally share the same learned weights or settings.
Forcing them to use the same core knowledge.
Kind of. Or parameter control, which might involve using the source model's parameters as a starting point for the target model, or adding constraints to guide how the target model learns. And model ensemble methods combine predictions from several different models, maybe trained on different aspects of the source data.
Getting multiple perspectives.
And deep learning has really supercharged this area. Techniques like RTL try to explicitly learn a classifier that adapts well, while also minimizing domain differences. DAM and UniverDAM use specific regularizers to encourage adaptation. For ensembles, we mentioned TradeBoost before, and there's also LWE, which weights models based on local relevance.
And the deep learning specific ones.
Loads of them. You have reconstruction-based ones like TLDA using deep autoencoders, and then a big group of discrepancy-based methods. These train deep networks, specifically designed to minimize some measure of difference between the source and target feature representations learned by the network.
Building the domain alignment right into the network's goal.
Exactly. Examples are DAN, DCoral, DAN, JAN, CAN, lots of acronyms.
DAN sounds interesting. Domain adversarial neural network. What's the adversarial part?
That's a really cool idea. You typically have two parts in the network: a main feature extractor doing the task, and a domain discriminator. The extractor tries to learn features that are good for the task, but also make it impossible for the discriminator to tell if the features came from the source or the target domain.
So they're playing a game. The extractor tries to fool the discriminator.
Precisely. It forces the extractor to learn features that are domain invariant, features that don't give away which domain they came from. Iwanda is an example used when the target domain might have fewer categories than the source.
That's a really clever way to force the model to generalize. Okay, we've covered a lot of the how. Where is all this actually being used? What are the applications?
Oh, it's being used all over the place now. The impact is pretty significant. Medicine is a big one. Medical image analysis relies heavily on it.
Like the pre-training you mentioned.
Exactly. Models pre-trained on huge data sets like ImageNet are then fine-tuned for specific medical tasks, spotting tumors in scans, assessing osteoarthritis from x-rays, computer-aided diagnosis. It helps overcome the scarcity of labeled medical data.
Makes total sense. What else?
Bioinformatics predicting protein functions, finding disease gene links, transportation, improving traffic flow predictions. Recommender systems are huge too.
How does it work there?
Cross-domain recommendation. Let's say you buy lots of sci-fi books on one site. Transfer learning could help a different site recommend sci-fi movies to you, even if you've never browsed movies there. It transfers your preference patterns. CSTM is one technique mentioned for this.
Learning my general tastes and applying them elsewhere. Okay.
Yep. Then there's communication tech, Wi-Fi localization, saving energy in wireless networks. Urban computing predicting good spots for new stores, transferring city planning insights. And tons of recognition tasks, hand gestures, faces, activities, even recognizing emotion in speech. Sentiment analysis, fraud detection, social networks, analyzing complex hyperspectral images. The list goes on.
It really is incredibly. So the survey paper also ran some experiments, right, to compare these methods?
It did. They focused on object recognition and text classification using standard benchmark data sets, Office 31 for objects, Reuters, and Amazon reviews for text.
Standard stuff. And what did they find? Did one method clearly win?
Well, not really a single winner, which is maybe expected. The results are in the figures and tables in the paper. What they showed is that performance really varies. Different algorithms do better or worse depending on the specific data set and the exact transfer task.
So what worked for transferring between, say, Amazon review domains might not be the best for the Office image domains.
Exactly. Feature-based methods, things like HIDC, SCL, SFA, MTRIC, SDA, they often performed quite well across different tests. But the main takeaway was really that choosing the right transfer learning model isn't trivial. It depends heavily on your specific problem.
No magic bullet, then. You need to understand your data and your task.
Precisely. The experiments really highlight that complexity.
Okay, so wrapping this all up after this pretty deep dive, what are the main takeaways for listeners about transfer, and where does the field go next?
I think the key thing is that transfer learning is a really powerful and practical part of modern machine learning. It lets us build on existing knowledge, which is crucial when getting lots of new labeled data is hard or expensive. As for the future, the survey points to several areas, applying it to new, complex problems, like maybe privacy-preserving scenarios.
That sounds important.
Definitely. Also, getting better at measuring transferability, knowing beforehand how well knowledge will transfer, and crucially, avoiding negative transfer.
Where trying to transfer knowledge actually makes...
Yeah, that can happen if the domains are too dissimilar or the method isn't right. Making the models more interpretable, understanding why they make certain decisions during transfer is another big goal, and just more fundamental theoretical work. But the big picture is clear. Transfer learning reduces that dependency on massive labeled data set, which is a huge advantage.
It definitely seems like a field with a lot of momentum, and Joel, this has been really insightful. And just a reminder for everyone listening, if this sparks your interest in learning more AI, check out the course at rajamanakam.com. Use the code KEYT for a discount.
Absolutely. Understanding transfer learning is, I think, becoming pretty essential if you're working in AI or even just trying to follow what's happening at the cutting edge.
Totally agree. Okay, so here's a final thought to leave you with, building on what we discussed. Given this growing ability for AI to transfer knowledge, but sometimes very different areas, what are some of the ethical considerations we need to think about as this technology is even more powerful spread? Something to chew on. Thanks for joining us on the deep dive.
Hope it was useful.
And remember, that discount code for the AI course at rajamanakam.com is ET. We'll catch you on the next one.